Hello again. Now let's start checking the design to the dynamic earthquake instead of the static one. And to do that, I'm gonna switch back to an older version of the building, which is the R2 version, where I had my columns pinned. Actually, I could go to the earlier version, which is when I had my columns actually fixed. Alright, so the first thing that we gotta check for the dynamic analysis first, we verified the masses already in the building when we were doing our static analysis. So look back on that video if you haven't checked the mass of the building yet. The other thing that is unique to the model analysis is actually the modes of the building. So to verify that we have analyzed enough modes of the structure to include all of the building modes in our dynamic analysis, we can go to display tables, and this time we could go to structure output, model information. We can look at the participating mass ratios and the model direction factors and the participation factors. And let's click OK. So a table would come up, and what we can do is we can switch to the participating mass ratios first. We can see that the first period was predominantly a rotation about Z. So if you look at the axis over here, UX is a building that is oscillating or vibrating in the X direction over here, which is in this direction. UY is a building that's vibrating along the Y direction. UZ is a building that's vibrating up and down. And then the R is the rotation. So RX is a building that is basically twisting in the X direction. RY is a building that is rotating in the Y direction, and RZ is a building that is oscillating in torsion direction around the plan. So our first mode, these numbers are actually weight or percentage. So you can see that the first period is mostly weighted in the rotation, which is the torsion oscillation of the building. So we can expect that our first mode is going to be a torsional mode in the y-axis, because that's where the weak axis of the core is. Our second mode was actually predominantly just oscillation in the y direction with a little bit of torsion again. Our third mode was just oscillation in the x direction, and so on and so forth. Now, if we switch on to actually look at the sum of these weightage, we can see that they increases with every mode until the last mode they reach how much in total that was accumulated with all the analysis modes that we've done. So the code specifies at least a 90% of the modes are considered. And we can see here that we've achieved 98% in the X, 97% in the Y direction. And the other important one is the torsion. We have actually achieved the 99% in the torsional direction. For me, I like to achieve at least 95% in these three. It's fairly easy to achieve that with not so many modes. So might as well achieve a higher percentage to actually have confidence that you have converged enough modes in your analysis for the dynamic earthquake forces that's going to be done later on. All right, so now we can start to look at the overturning moments at the base, like what we've done with the static earthquake force. We can go to display, story response plots, and we can look at the overturning moments. This time we are switching on our earthquake dynamic load case. And we are looking at the limited ductile load case, which is this one. As we can see here, we are getting about 93,300 overturning moment. If we actually compare that with the static load case that we were looking at earlier, again for the limited ductile, we're getting 100. Sorry, this is the dynamic load case still. The static, which was this one, we're getting 145. And with the dynamic, we're getting only 90. And the reason that is that instead of actually looking at the moments, if we look at the story shears, if we look at the static force, we actually have bigger shear forces applied higher in the building. But if we look at the dynamic load case, we actually have the opposite. We have a little bit of high load up here, but then the loads are fairly small within the middle height of the building, and they increase again at the base of the building. Now, the width of this step is how much shear force is applied at each floor. So you can see here it's quite small. It's a bit high on the top because of the weight of the building that we have, the heavier roof that we have, and it reduces at the bottom. And because of this distribution of the shear forces on the building, that actually reduces your moment, because that brings your action force, instead of being up here, for example, you can bring it down here closer to the ground. So that reduces your overturning moment. So we end up with 90 something thousand instead of 145. Now that is a big difference in the analysis, and it actually reflects how the building is going to behave. And the code recognizes that. The code always says that if you can do a dynamic analysis, do a dynamic analysis. You can always choose a higher design level instead of using the static. Just because it gives you less force doesn't mean it's actually less conservative. It's actually more realistic, because it considers the modes of the building and how is the building going to vibrate when the dynamic earthquake waves arrives at the building location. So we've had a look at our overturning moments and our shear forces. We have we can actually compare them. So we can go to the table, and instead of looking at the model results, let's actually look at the base reaction. Let's make sure we select the load cases that we want to look at. We want to look at the dynamic limited ductile and compare it to the static load case in the X direction and the static load case in the Y direction. Okay, so with the static, we're getting 5,600 base shear in both directions. With the dynamic, we're getting 5,000 in the X direction and 3,200 in the Y direction. And the reason that with dynamic we have bigger shear force in the X direction is because the cores are more stiff in this direction. So they actually can resist the vibration better, and more stiff building will attract more earthquake force. So that direction is more stiff, it attracts more shear force. That direction is more flexible because it's the weaker axis of the cores. So it actually makes sense that it's attracting less shear force in that direction. Now, in Australian Standard, we don't need to modify any of the parameters for the dynamic earthquake analysis, but in other codes like the American code, for example, you will need to scale up your dynamic analysis so you at least achieve the same base shear force as your static analysis. That is required in some codes. It's not required in Eurocode as far as I know. It's not required in the Australian standards as well. So once we have satisfied the number of model mass participation, which we just checked was 98% or thereabout, we're good to go with the analysis, and we don't need to modify it any further than that. And we can just use that straight away to design. Now, the second thing that we need to do now is to start looking at the core walls and start cracking them, like what we did with the static load case. Only this time, if we go to shell stresses, or combinations, is much simpler, because in fact we only have one load combination, which is this one, G plus 0.3 cube plus the dynamic earthquake non-ductile system. We can look at the maximum stress, the maximum stresses in the S22 direction, and again that was 0.6 times the square root of 50 MPa. Now, we didn't need all of these load combinations because the dynamic analysis from Etabs actually considers the eccentricities on each member when it does the analysis, and the results it give you is an envelope of the different modes that were applied on the building. And for that reason, we don't need to do those earthquake combinations with 0.3 EQ plus and minus and things like that. If you recall, when we defined our dynamic load case, which I'm going to open up right now, we included this combination type, an absolute combination, which means it combines 100% from one direction and 30% from the secondary direction. and it reports the overall result to you. And we've actually included a 10% eccentricity in our dynamic analysis as well. So it envelopes all these results and it gives you an output of only one result. So it's actually faster to analyze in Etabs than the static one, believe it or not. I think we're looking at the wrong load case here. We should be looking, at this one. Okay, so like what we did with the static, these ones look like they crack. So what I'm going to do is I'm going to select them and I'm going to assign them to a group. I'm going to create a new group and call it crack or walls. But this is the dynamic one. All right, and let's just add them to the group. Let's switch on the elevations and see the other ones. This one doesn't crack, only probably just the lowest floors. This one over here is cracking. This one similarly, it only cracks down here. This one, the whole thing is cracking. This one again, I would say the whole thing is cracking. Same here. This one is cracking only up to here. Actually, that was already selected. Okay. Those ones don't crack. And those ones also don't crack. Those ones are very, very peak stresses at the corners, and it's very close to our 4.3. I think it's fair to say that they don't crack as well. All right. Next one. These ones don't crack. Oh, that one cracks here. Okay, that one cracks. That one doesn't crack. That is all good. Doesn't crack. That one cracks. Okay. Next one. We're looking at the whole thing cracking here, except perhaps this one, no. This one, no. These ones, no. 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 Actually, these ones crack here at the left-hand side. Okay, yeah, we'll leave them as cracking. The next one. Again, we have bit of cracking at the end there, so we have to crack the whole thing. All right, so these are the ones that crack. Let's assign them to our group and let's erase our analysis and let's select the ones that actually cracked. So how we select the group, and we go and define our wall section for a cracked wall. So we add a copy. What we need to do is go to the modifier and assign the 25% stiffness reduction. And let's then apply this wall section to the ones that we have selected because they cracked. Okay, let's rerun the analysis now. So now we've identified the ones that cracked. The next thing that we need to see is how much is the contribution of the framing action versus the contribution by our core walls, which is what we're going to look at in a minute. Okay, so my analysis is done now, and I'm going to switch to my 3D view and look at my overturning moments that's taken by my core. So I'm going to go to the dynamic load case for non-ductile. Actually, we can look at either one. Let's look at the limited ductile for now, and let's look at the M22 for the piers. And if we click here, we can see that this one is taking about 9,300 overturning moment, and this one is taking about 5,750. So their total is 15,000. If I go here and I look for the earthquake limited ductile overturning moment, I could see that my total overturning at the base about the X direction is actually 18,300 and my cores are taking 15,000. So 15,000 out of 18,000 is about 84%, which I think is pretty good. If you want to put more loads on the core and for the consistency of what we've done with the static analysis, let's do that so that we are consistent in terms of the forces and the drift that we're going to check soon. So let's save as this file and let's put it as R4, and this is the best office project with pinned columns for the ductile and for the dynamic analysis. Again, like what we've done, we're gonna toggle on our columns and switch off our walls and openings. We're gonna select all of our columns, go to assign, frame, release, and we assign top and bottom, click apply, and then we want to make sure that the lowest floor columns don't have releases at the base to avoid instability problems in the analysis. And we are going to rerun our analysis now. So my analysis is done, and now I'm going to switch back on to see my walls and switch off the columns, and I'll look at the pier forces again to double check how much are my cores taking now. So the first core now is taking 8,984 kilonewton, and my second core is taking 5,825. That adds up to 14,800 overturning moment. And let's check how much was my design. The tricky part is that my design moment actually reduced. Previously it was 18,000 because I had the columns fixed with the slab, and that was providing some stiffness and frame action. So that was providing stiffness, so that attracted more earthquake. But now after I've pinned them, what happened is the building became less stiff. So it attracted less earthquake forces, and my overturning moment went down by about 1,300. So my overturning on the core now, which is 14,800 in a comparison to the global overturning moment of 15,731, is about 94%, which is consistent with the results we got from the static earthquake analysis in terms of percentage. We're getting 91% over there. We're getting 94% over here. So that's a pretty good result that our cores are taking all of the lateral loads of the building. Now, the tricky part, let's start checking our drifts of the building. So let's go to story plot responses again. This time let's switch to diaphragm drifts, and let's look at the dynamic non-ductile load case. And as we can see here, we are getting about 0.005, and if we reverse that, that is a height on 186. So straight off the bat, a height of 186 passes the height on 66 requirement of the code, but I think it's a little bit high. So what I would like to do here is switch on my P delta analysis just to make sure that my design forces and my drifts are still within the limit, and I design for the secondary effects of the building because it looks like it's deflecting a fair bit. So I'm going to unlock the model. I'm going to go to define P delta analysis. Let's add our load cases. So we add our dead load, superimpose dead loads, 30% of the live loads. Now we don't have a dynamic earthquake load case option to add in our P delta in Etabs. So what we can do is we can use the static load case and we can factor it up based on how much it was equivalent to the dynamic case. So we've seen that in the X direction, it was almost the same. This is a limited ductile case, so we need to factor it up by 2. And in the Y direction, it was about 65%. So we can say it's a 65%, but we'll factor it up by 2. And we'll add that, so it comes up to 1.3. Now we've added equivalent static forces to represent the dynamic earthquake results that we were getting for our P delta checks. let's run our analysis with a P delta, and again that might take a few minutes. So the analysis is done here, and if we start looking at the drifts again, now it has gone up from 0.0053 to 0.006544, which if you inverse it gives us a ratio of around height on 152, which still safe and passes the limit of height on 66 required by the design code. What I'm doing here is I'm actually checking the maximum one only, which is this one. But what you should really be checking is you should be taking a square root of the summation of the two of them. So what you should really be doing is this was the worst one that we had here. So you should take 0.005556 square, and you should add the x direction drift, which is 0.00417 square. Actually, the one above at level 5 is higher, which is no, that's correct. Level 4 is the worst. 4417 square, and then you square root the sum of the squares. That gives you 0.007, and if you inverse that, that's still higher than 140, so you're still fine, but you should always be looking at the square root of the summation of the squares of the drifts in each direction. So in conclusion, that means that our 200 thick cores work for drift without having to thicken them to 300 thick, and without having to add the header between the two cores using the dynamic analysis. In comparison, when we did the static earthquake analysis, we needed to thicken them to 300, and we needed to add the headers just to achieve height on 130, which is still worse than height on 150 or height on 140 that we're getting from the dynamic analysis. So for that purpose, I always prefer to run with a dynamic analysis rather than running with a static analysis. One, it's better representation of the actual behavior of the building, and two, it's less conservative when it comes to the design of the cores of the building. And that's why you can have the same exact building and you can end up with two lateral stability designs. One of them might seem heavier than the other one, or depends how you look at it. The other one might seem that it's may not work, but they're both compliant to the code. One is designed to the static earthquake and one is designed to the dynamic earthquake. But obviously, I prefer to always take the dynamic analysis for earthquake for that purpose, and I'll leave it up to you to choose which one you want to go ahead with. Now that we have finished our wind analysis and checks, earthquake analysis and checks, the last thing that is left to us to do is to design the walls and the columns either manually or either using Etabs. We will explore that in the next module. So until then, practice these few checks and I'll see you in the next module.